Hello, I'm Bak from Kai's Lab. The presentation title is 3D hand tracking in the presence of excessive motion blur. This is joint works with Antoine Sarajos from University of Crete and Force, and Juyoung Lee and Untaek Woo from Kai's Lab. I'm going to introduce background of this study. As you see the figures, the hand-based interaction is useful in various applications, such as virtual object manipulation and collaboration with a remote user and sign language in AR/VR. So hand tracking is necessary to support the interactions. Many existing methods use depth camera as a sensor, so the goal is to estimate hand pose parameters from a depth image. The input is depth image as observation, and the output is hand model parameters, which is rendered to a hand model. There are some common challenges. First one is high degree of freedom. Hand model can be represented from 26 degree of freedoms, 6 degree for palm, and 4 degree for each finger. So we should estimate hand pose parameters in high dimension. Second one is self-occlusion. Because the hand object is highly articulate object, there are many cases of self-occlusions. When you see the side view of the captured depth image, some joints aren't observed. Another challenge is similar shape. Each finger has similar shape and length and thickness. So there is no feature to distinguish each finger. Existing methods already successfully estimate hand pose parameters in some situations, but our target situation is different. We introduce additional challenges in this research. First one is temporal discontinuity. In the video, hand rotate fast. In this motion, the temporal continuity is broken. Actually, some existing methods have already addressed the temporal discontinuity by fast hand motion. However, when you capture a single image during fast rotation, the depth image is severely contaminated by motion blur. Given the contaminated image, most existing methods are likely to fail to track the hand, which gives wrong interaction in AR/VR. There are many related works for hand tracking algorithms. According to existing category of hand pose estimation, we also categorize the methods into generative and discriminative and hybrid methods. Our viewpoint is two. First one is temporal discontinuity, and the second one is motion blur. Generative approaches estimate hand pose parameters from rendered hand model. They assume that the hand motion is slow and smooth, but in fast motion, the assumption of temporal continuity is broken, and they fail to track the hand pose in the presence of motion blur. Discriminative approaches are able to estimate the hand pose in a single frame, so they don't have to assume that the hand should move slowly and smoothly. They more focus on the generalization beyond the trained dataset. However, in very fast motion, the motion blur is generated. In this frame, they may fail to estimate hand pose. Hybrid approaches combine the merits of generative and discriminative approaches. They can reinitialize the hand pose from detection method or learning method, despite fast hand motion. So, temporal discontinuity is not an obstacle for the approaches. However, in the presence of motion blur, it may fail to track the hand pose. Especially in model work, it estimates successfully hand pose and shape in strong two-hand interactions, but they say a limitation by motion blur. Some existing methods already address common challenges and temporal discontinuity problem. However, to the best of our knowledge, there is no previous works to track the hand pose in the presence of motion blur. Our goal is to track hand pose parameters with temporal discontinuity and motion blur using a depth camera and a gyroscope. The gyroscope is attached to the back of the hand, and the depth camera captures the gyroscope on hand. Our algorithm can be divided into offline calibration and online sensor fusion hand tracking. First, we calibrate time delay and coordinates between gyroscope and depth camera in offline process. Because they have different coordinates and timeline. And then we employ hierarchical particle filter for sense fusion and tracking in online process. For calibration in this step, we estimate pose offset between camera and gyro coordinates. As the figure, we can define two offset quaternions O1 and O2. HCT is a hand pose from camera reference frame at time step t, and HGT is gyro pose from gyro reference frame at time step t. Next step, we define delta of HC from initial pose at time step 0. We can represent this using gyro pose and two offsets. Then we finally formulate delta of HCT as one offset of 2 and delta of HGT. We can reformulate this as homogeneous matrix form. Finally, we can express matrix H and vector O2. We can simply estimate offset O2 with singular value decomposition. Next, we estimate time delay between camera and gyroscope. To do this, we repeatedly rotate the hand for a period of time with fixed translation and finger parameters. We use the depth images from depth camera and render the hand model from gyroscope. So we can estimate the optimal time delay, minimizing the sum of errors. Finally, we get pose offset and time delay between depth camera and gyroscope. Next, I'm going to explain the hierarchical particle filter for sensor fusion hand tracking. We employ the existing method from Macris work from POS. In the dynamic Bayesian network, the state xmt-1 represents full hand pose parameters in the previous frame, and GT0 and GTN is multiple gyro poses. Because the gyro sampling time is faster than camera sampling time, we can get more gyro poses in a single depth frame at time step t. And X0T represent translation and rotation for palm. And the states from X1 to X5 represents the space of each finger. And the state XMT is final state for full hand pose parameters at time step t. To explain our algorithm, we should first explain observation likelihood. To that, we first define a cost function ED to calculate the error between the depth image and the rendered depth map from each particle. EG represents the error between the hand rotation of a particle and the calibrated gyro pose. Final cost function is a weighted sum of the ED and EG, and the weight is calculated by the gyro angular velocity speed, which is empirically decided. In this step, we exploit the fact of that fast hand rotation generates motion blur. When motion blur is generated, the cost function more relied on the EG, and when the motion blur is not generated, the cost function more rely on the ED. And so the better formulation to detect motion blur is in future work. So finally, we can easily change the cost function to likelihood. Finally, we can calculate the weight of each sampled particles as a observation likelihood. The figure shows the sampled particles. We sample 64 particles and render them for the observation likelihood. Because we use multiple gyro poses, we can sample the particles with slope-based sampling. For the slope-based sampling, we evenly sample the particle poses from the previous solution and the gyro poses, and then we resample the particles from the observation likelihood. Next, we one more sample the particles from the updated state S0 with a normal distribution, because slope-based sampling is limited to gyro trajectory. So we finely tune them one more, and then we resample particles again. And the particles for each finger are sampled from the solution in the previous frame. And we repeatedly conduct the resampling, so in this context, the finger movement relies on the previous frame, so our limitation is that we don't address the fast finger movement. We finally sample particles for the full hand pose parameters from each updated auxiliary models. Then we repeat the particle filtering. We get the final hand pose parameters from average of the resamped particles. We first have an ablative study. As our basic method, we employ the Marquis walk, and we add some components, slope-based sampling, and gyro regularization. The left graph represents the percentage of frames of finger tip error within a threshold in our self-data set. As shown in the graph, we can conclude the fusion of slope-based sampling and gyro regularization is best result. So we adopt all components for our method. This is a qualitative result to show 3 consecutive frames in fast rotation. As you can see, the proposed strategy shows best result and individually selecting each method. We observe that IR image for SR300 camera is not broad, so the IR input is used to measure the 2D position for ground truth using a reflective marker. Next, we compare our method to state-of-the-art method. In the frames of slow motion with temporal continuity, the all method shows adequate accuracy, which is represented in left bar for each method. For fast motion with temporal discontinuity, the performance of generating method drops considerably. This is natural because they assume that the hand motion is slow and smooth. Our method also employs model-based tracking, so the performance drops likewise. In this sequence, the discriminative approach chance walk shows best result because it can estimate hand pose in a single frame. So the temporal discontinuity is not obstacle for the method. In very fast motion with motion blur, even though the discontinuity method chance walk exhibit best result in the previous sequence, in this sequence motion blur considerably affect the method because the trained dataset does not include motion blur. Finally, our method outperformed the other methods in this sequence. We release the dataset in the link. This is a qualitative comparison result. When the hand rotates fast, motion blur is generated like this. When some joints are blurred, the performance of other methods are dropped, but our method shows adequate result. And another frame is like this. Yes, a similar result. Yes, there is a motion blur and similar result. And this is some more example for qualitative result. We observe that some parts of the finger are blurred in fast rotation. So this is image artifact effect to the existing method, but other method exhibit good result despite our method exhibit good result despite motion blur. This is a simple application in Unity 3D. The camera is attached to the HMD on user's head. We pinch the virtual object and fast rotate them. Even though motion blur is generated by fast hand rotation, the user can interact with the virtual object. Our limitation is that we address the hand tracking in the presence of motion blur by only hand rotation, because gyroscope can measure angular velocity of the hand rotation. Another limitation is that we assume that the camera does not move much and the hand remains within the camera's field of view. In summary, we propose the sensor fusion method to track the hand pose. As the method, we formulated it using hierarchical particle filter. In the experiments, our method exhibited accurate performance despite fast hand rotation and in the presence of motion blur. This is the end of my presentation. Thank you for listening my presentation.